Hello, today we're going to show how a discrepancy between a measured result and a theoretical result using Newton's law of gravity and his second law led to the discovery of dark matter. Dark matter makes up about 96% of our universe, and no one really knows what it is. It's not the same as the 100 or so chemical elements that make up the matter on Earth and in the visible universe. So what we have to the right here is a planet of little mass m orbiting a larger mass given by large mass m. In the case of dark matter, the smaller mass might be an individual star orbiting on the outer fringe of a galaxy, or at least farther out than all the stars that this little mass m's orbit include. So from Newton's universal law of gravitation, we can write this equation that the force of gravity given by this formula equals the centripetal force of little mass m in its orbit of radius r. Here we're taking r to be the distance between the centers of large mass m and small mass m. So you might recognize this is just Newton's second law, where all the forces on mass m is given by the universal law of gravitation. So we can simplify this formula just solving for v. We do that by first reducing the power of r. We can multiply each side by r, and then we could divide each side by m, and solving for v, we get big G, which is Newton's constant of gravitation. And then since we had v squared, we have to take the square root of each side. So what this shows is that the velocity v is related to r by 1 over the square root of r here. So for the moment, I'm just ignoring big G, big M, because in our calculations, this number G times M would just be a constant and not be important for the result that I'm trying to show here. So if you graph 1 over square root r, the velocity, you get a velocity curve that slopes downward here. So we could make a little table just to show how that lower curve was arrived at. So say as r is 25 in some distance units, then the square root of 25 is 5, so the velocity would be proportional to 1 over 5 in these units. And then say that's out there someplace. So you could get a point on the curve where this was 25 and the velocity was 1/5 here. So we can do that again. Say r is 16, which might be here. So the square root of 16 is 4. 1/4 is 1/4. So that would be about up here. You get a point on the curve right there. So you could keep doing this. You know, if r is 4, then the square root of 4 is 2, so you get 1/2. So that would be, you know, you're going to get a higher point here. So just from Newton's laws, we come up with what they call a rotation curve. So this is the theoretical rotation curve. But when the velocities of the outer stars, here I've only used one, you know, there's millions of stars, their velocities can be determined by spectrographic methods. And when that was done, they were all found to be going at the same velocity. So that's the discrepancy. This is an experimental result. And this is the theoretical result. So it's believed that Newton's laws are valid under the conditions of this. It's a non-relativistic effect. So to explain this discrepancy between experiment and the theoretical result, the hypothesis of dark matter was made. So again, dark matter, they believe, makes up about 96% of the universe, and no one really knows what it is yet, although there are hypotheses to explain that. So anyway, this just shows that some knowledge of the basic laws of physics can help make large new discoveries.